Thank you, Luke, and good day, everyone. My name is Vince, and yeah, today I'd like to speak about some features of Flownex with regards to secondary air system modeling. Today's presentation will start off with a small introduction to Flownex, talking about the software and some of the actual kind of features of it. Then I'd like to move on to discussing some of the secondary flow components, talking about some of the theory and the configuration of these components. And then towards the end of the presentation, I'll be talking about two demonstration models, one being a secondary flow path, where we look at using quite a lot of the components inside of the library. And then after that, I'll be looking at a model where we looked at optimizing the geometry of a small secondary flow path by using the parametric study tool inside of Flownex. So Flownex itself is a commercial system simulation software code. It's a 1D code, and by that we usually mean it's a one-dimensional flow and two-dimensional heat transfer code. So we have one-dimensional flow elements all connected together to form networks, which ultimately build up the flow inside of our system. These elements contain equations for mass, energy, and momentum conservation, and are solved using a CFD pressure correction algorithm. This gives us very fast solving times and very high stability for our solving. Flownex has a lot of built-in fluids. These include incompressible fluids such as liquids for modeling cooling or lubrication systems, as well as fuel supply systems for turbomachinery. We have compressible models for modeling your primary flow as well as any secondary flows, and can also basically include mixtures of gases and liquids for the purposes of modeling combustion or combustion products. We understand that a lot of our users have their own in-house correlations for pressure drops or for heat transfer, and as a result, we've put a lot of effort into ensuring that these correlations can be inserted into the code in a user-friendly way. So we have a lot of options available to users, and are then able to basically develop small custom components that users can use, and then package those inside of your own company database. So all of this can be done with minimal effort from the user, and then shared across an entire company for use in all of your models. The software itself is designed within an NQA1 and ISO 9001 environment. This is basically high levels of quality control, ensuring verification and validation of our software. In terms of the gas turbine design or secondary flow path design, Flownex is ideal because it gives us very good estimations of the flow during the initial design stages of secondary flow paths. So we're able to calculate mass flow splits through secondary air systems. This is a result of the pressure conservation or the momentum conservation inside of our governing equations. So we can have multiple 1D paths all connected together and predict the splits of flow between these paths based on the different pressure drops in the different directions. Also taking into account the varying pressure drop correlations between multiple components, as well as the varying pressure drops that we see with changes in radial position inside of our turbines. We understand that this is an environment where CFD can also be used. However, during the initial designing of secondary flow systems, CFD solutions are seldom used due to the requirements of very specialized personnel and the large amount of time that it takes to set up and run these models. So these one-dimensional networks become very flexible in this environment, as you can configure them and modify them very easily. You don't have to modify CAD files, for example. And there's no meshing required, so the variations in the design are very quick, along with the solving times, which give a lot of flexibility to engineers in the initial design stages. We're also able to look at characterizing the flow rate versus pressure drop in a very detailed manner. We can take into account each of the geometric features inside of our secondary flow paths, be it seals or small cavities with rotating walls. We take into account effects such as windage, temperature rise, and heat transfer from surfaces. So we can develop a a very well-structured one-dimensional model of the flow paths, giving accurate results for initial sizing calculations. So there are a couple of limitations in assumptions that need to be made on the geometric side sometimes, but overall the systems can produce accurate results for initial sizing for use in optimization of the design in the early initial stages of secondary flow system designs. We have quite a set of components for our secondary flow modeling. We have, in this case, a rotating components library. Inside of this library, we include components such as vortices, both free and forced vortexes. We have a couple of models for seals, in this case, maybe a labyrinth seal model. These can be considered either as lumped models or considered per tooth, for example. We have models for cavities with different rotating plates. One, perhaps we would have a cavity with both plates rotating, in which case we'd be using a rotor-rotor cavity, or perhaps one cavity rotating while one is remaining stationary, in this case a rotor-stator cavity. We also have models for nozzles and rotating gaps in our system, as well as rotating channels, where we have flow moving from different positions inside of our secondary flow path. So perhaps moving radially inward through a rotor section. In this regard, we would be having body forces on our fluid and windage power transfer. All of these effects are then captured inside of these components, and all the relevant results are made available to the user as well. In the cavity models, what we basically do is consider a control volume inside of this almost stationary space compared to the relative flow around it. Inside of these spaces, we do a moment balance inside of the fluid, taking into account moments from bolts mounted on the stator or the rotor. We take into account viscous forces of the fluid on the shroud and the fluid on the walls of the cavity. We can also take into account different shapes of the walls. So the walls don't need to be considered as purely radial discs. They can be considered with the actual wall geometry, taking into account any recesses, for example, being able to, with very easy inputs for the users to specify these profiles. We can take into account, as I mentioned, the effects of some bolts inside of these cavities. We have a couple of correlations already inbuilt into Flownex for drag coefficients, so users can simply select the number of bolts as well as information regarding where they're mounted and the size of these bolts, and Flownex then provides the relevant correlations for drag coefficients, and then uses this in the moment calculation when calculating the swirl inside of the cavities. We're also able to discretize our cavities. So you can take a cavity, for example, and discretize in the radial direction, having individual swirl calculations done per increment, and then also having different results available for those in terms of pressure or temperature, for example. Other components can then be connected to these increments for use in flow through the cavity. So they can be connected at different radial positions using different swirl values for their inlet and exit conditions. Our labyrinth seal models can be for both axial and radial labyrinth seals, with either straight or staggered orientation as well. As I mentioned, we have the ability to look at a discretized model, considering each tooth individually, or looking at a lump model for more simplified cases. These flow components also account for choked flow, so if our critical pressure ratio is ever exceeded, the flow is choked inside of our flow calculations. And then also, as I mentioned, we have the ability for users to specify their own correlations. In this component, for example, users are able to specify their own values for discharge coefficients, as well as kinetic energy carryover coefficients as well. When it comes to modeling nozzles, there are a lot of parameters that we take into account. First off, the incidence angle of the flow entering the nozzle, as well as the length of the nozzle, either to model it as a long or a short orifice, and then taking into account the inlet geometry to that nozzle, be it a sharp entry, a rounded entry, say a chamfered entry, or a filleted entry. When the nozzle itself has a change in radial position, power transfer becomes an important consideration. In this regard, we calculate the body forces as well, and then also make windage power results available for the user. Rotating channels are similar to rotating nozzles, but we tend to use these when modeling cooling flow inside of turbine blades. So here what we'd be doing is modeling for example, we'd be modeling the flow through the cavities inside of the blade. We have correlations implemented for frictional pressure drops for both ribbed and pedestals, as well as the heat transfer correlations for these features as well. We also take into account body forces on these components and have a fully flexible orientation available. So the users can specify purely axial flow or purely radial flow, or a combination of the two. The specification is entirely arbitrary as well. These components can be discretized as well if it's required to see results along the length of these channels. And as I mentioned, power transfer is also calculated in these components as well. For more information on some of the blade cooling and combustor models, we have webinars available on these. If you go to the Flownex, if you go to our website, flownex.com, and go to the webinars page, you'll see recordings of past webinars. And recently we've had webinars on blade cooling, where we look at modeling the internal flow of a blade using Flownex, and then use a coupling between Flownex and Ansys Mechanical to model the heat transfer, and use Ansys Mechanical to basically model the temperature distribution throughout that blade. We also have a webinar on combustor design using Flownex, where we talk a lot about the different heat transfer correlations that are shipped with Flownex, some of the components that are available out of the box, as well as some of the details regarding our combustion model as well. As I mentioned, we have the ability to include custom correlations. So here we have an example where we wanted to include the custom correlation for an axial swirler. You can see the correlation there for mass flow as a function of the pressure difference and a couple of other variables. In this regard, we had put this correlation in a script, for example. In Flownex, we use the C# language. This can be connected to our flow component, and this basically forms a small little box in which we're able to define our own correlations. This can be wrapped inside of what we call a compound component. You can add your own custom image, and then this will appear along with all of your other components in your Flownex library. So you can drag and drop this in future models. You can even connect this, or even put this component on a server drive and then share this across your company, having a standard company database available to all your Flownex users. So this allows a high level of standardization in all of your engineering work. If the C# language is a bit intimidating for you, we do have a couple of other components available, notably the Excel component. This basically allows you to define your correlations in an Excel environment and then transfer data between your flow components and your Excel calculations relatively seamlessly as well. We also understand that values for flow and for temperature are not always the end result that an engineer is looking for. Often we're looking to size a channel for a particular flow rate, or adjust a flow rate until a certain temperature is achieved. So we've added a lot of design and optimization features above the solver itself. These include the designer, which works very similar to the goal-seek function inside of Excel, where you specify a target value and then an input variable that Flownex can change. Flownex will then change that value until the target value is achieved, and this can also be done for multiple variables. We have an optimizer as well, which works very similarly to the designer. However, instead of achieving a target value, it either looks to minimize or maximize this this value that you input. We also have two options for sensitivity analysis. The first one being a parametric study, where we look at specifying individual cases in an Excel environment. I'll talk more about this in a second. Or alternatively, using a Monte Carlo analysis, where we look at specifying a minimum and a maximum value, and then having Flownex generate random data according to a distribution, so perhaps a uniform or a normal distribution, for example. This information is then inputted into our flow model, and the results are saved for analysis later, so we can characterize the sensitivity of particular inputs on key results of our model. Okay, so just before I jump across to some of the demonstrations I have already, I'd like to just give a recap of what I've spoken about. So Flownex itself is a commercial code. That basically means that all of the development work, as well as maintenance of the software, is managed by us directly. As a user, you can focus on the engineering work and not on the maintenance and development of your software. The code itself is very easy to use. It is a very user-friendly user interface. And after a couple of days and a few training videos or a short training session with one of our technical staff, you can become very proficient in the software. The tool itself is built on one-dimensional building blocks using conservation equations for mass, energy, and momentum. So this allows us to have incredibly fast solving times, which also gives us a lot of flexibility in the optimization of our designs and analyzing the sensitivity of some of the inputs to our final flow results. As I mentioned, Flownex can be coupled to ANSYS Mechanical. It has a couple of other codes that we can couple to directly, but above that, we have a API which allows us to couple the Flownex code itself to almost any other Windows application. So if you're looking to do any post-processing or perhaps co-simulation, this can also be included through our API. Our components employ standard industry correlations, and all of them are provided with detailed documentation. This is shipped with Flownex, so users are able to see exactly what theory has been implemented in a component and exactly what the limitations on the correlations are. So the code is by no means a black box code. All of the information regarding the theory has been shipped with the software itself. We have the ability to specify custom correlations for heat transfer and pressure drop, as I mentioned. We've got a large built-in fluids library with the ability for users to import their own fluids as well. We have importers for fluids from NIST or RefProp, as well as other importers such as Cape Open. As I mentioned, the software already has a very fast solving time, which gives us a lot of flexibility in running multiple design cases. And lastly, our software itself is developed very much in line with our user feedback. So we communicate very closely with our resellers, and through them we're able to gauge exactly what components are being used by users and receive requests directly from our user bases. This information gets fed directly back to the developers and is included in the development plans for the upcoming development cycles. We typically have between 2 and 3 releases per year, which results in a relatively rapid implementation of new features that users would like to see inside of the software. Okay, so I'm going to move across to one of the models I've prepared. This over here is a secondary flow model inside of just a kind of standard turbo machine. We have a compressor on the left here, which is then we have a tapping point where we have some cooling flow moving around the outside of the machine and then re-entering in the high pressure turbine stage, one of the very first stages. On the left with our turbine extraction point, our compressor extraction point, we specify some boundary information regarding this exit point. The pressure can be specified as either a total value or a static value, depending on which one you have available. And we have a lot of flexibility in terms of the units that this can be specified in. All of our input units for geometry as well as fluid variables are available in both metric and imperial units. So whichever you're more familiar with, chances are that unit's already inside of the code. We also specify a boundary condition for swell, so capturing the rotational velocity of our flow. We then have a restriction component to account for the losses into this very first cavity. The cavity over here we're modeling as a rotor-stator cavity. We're able to input all of the geometric information for the size of that cavity, and then are able to see results for information such as the swirl ratio, the windage power transfer, and then more detailed results such as the individual moments on the rotor and stator themselves. Following the flow path, we have an annular flow gap or rotating annular gap. This one here, we're able to just specify the inner and outer radius of this rotating gap, and Flownex calculates the necessary pressure drop through there. We then have a cavity at the top here with nozzles at the inlets and outlets. These nozzles are modeled as sharp inlets. So the profile at the inlet is considered sharp here. We then specify the diameter and the length of these nozzles and the orientation of the nozzle itself. So in this case over here we have a radial nozzle and on the right an axial nozzle. All of this information is used in calculating the discharge coefficient and the effective pressure drop over that component when used in calculating the airflow distribution between these branching paths in our network. We've then got a labyrinth seal over here. In this case, it is a straight seal with an axial orientation. We input information regarding the number of teeth and the geometry of the teeth, and then either choose to model this as a discretized model or as a single lump model. And we're then able to characterize the pressure drop over each of the teeth for use in our flow calculations. If we continue with our flow path, we see similar components being used to characterize the different geometric elements. We then get up to the end of our model where we have our inlet into our turbine stages. Over here we have some custom correlations specified. So there are two scripts employed over here. The scripts are reading in fluid variables from the neighboring elements through these data transfer links, and then doing a calculation for a discharge coefficient and transferring that value back to a restrictor. So we're able to implement our own correlations here in a relatively easy style, which is very easy to adapt as well. So if the correlations ever change, or if you would ever like to reuse it, it's relatively easy to edit as well as to copy and use in another project. Okay, that about sums it up for this model. Our solving time on this model, just out of interest's sake, is about a half a second. We only have in this model about 20 flow components, so it's not by any means a large model. However, as the number of elements increase, we typically only see our solving times vary between, say, 1 and 10 seconds. So we're able to get very rapid execution of these models, which gives a lot of flexibility in the optimization of the geometry. That kind of leads us on to the next model over here. What we have over here is a benchmark that we did for one of our clients. It is modeling the flow from a compressor extraction point through a radial inward flow channel. There are 30 of these channels connected circumferentially or equally spaced around the circumference of this rotor. This flow then passes into a cavity, then through a small flow path into another cavity, and then through another small flow path before exiting to be used later. What the aim of this benchmark was to calculate the optimal angles for alpha, for beta, and the diameter of this hole. Alpha in this case is the angle that this hole is inclined at in the axial direction. Beta is the inclination angle in the circumferential direction, and then looking at the diameter of the hole as well. So when it came to modeling this, it was simply just adding boundary conditions for our inlets and outlets. In this scenario, the goal was to calculate the optimal angles for a given mass flow to achieve the lowest pressure drop through the system. So we were able to specify a mass flow boundary condition at our outlet, along with our inlet boundary conditions from our compressor extraction point. The flow inwards was modeled with our rotating channel. Here we're able to specify our 30 channels in parallel, as well as all of the information regarding the geometry of those channels. In terms of results, we're then able to look at the power transfer in this channel. So because it's a radial inwards channel, we see some excess power, in this case in the order of 770 kilowatts roughly. We're also able to look at results such as velocities. So we can see in these flow channels we have a velocity of about 149 meters per second. So we can expect quite large friction losses inside of these channels. For the cavities themselves, we've used rotor-rotor cavities. These cavities have then been discretized in the radial direction. So we can actually take a look at the swill ratio as well as the other fluid variables at different radial positions inside the cavity. To do that, we just simply look at the results of each increment. So I'm just going to take one of the middle increments, for example. we can see the swirl ratio of about 2.55 with all of the other variables for our rotor moments and fluid variables such as pressures and temperatures. Following there, we just simply have some rotating channels connected to our another rotor-rotor cavity. There are a couple of scripts included here. Just to let you know, those scripts are not used for any custom correlations in this case. They're just simply used for a bit of pre-processing before the simulation. By changing some of the inputs, we needed to do a couple of changes. The specification for the angles, for example, didn't match the natural specification inside of Flownex, so a couple of conversions were required, but they're relatively easy to configure anyway. To test the different cases, what we decided to do was use a parametric study. By doing this, we're able to vary the angle alpha, beta, and the diameter of the hole and see what effect this has on the total outlet pressure of our system. We define each of our cases that we'd like to test in rows, where each of the columns represents one of the variables we would like to change. So this first column, for example, represents the angle alpha, as you see on this drawing over here. The angle beta and the diameter as well are also varied. What happens is all of this information is transferred to the flow network. The network is solved in steady state. The results are stored, and then Flownex moves on to the next row inside of this table. So we can very easily specify multiple conditions for different runs in our parametric study, and Flownex will automatically change between these different parametric cases, storing the results for each of them as well. The results are also stored in an Excel environment. What we have over here is just storing our results for each of the variables that I mentioned, the angles, the inlet properties basically, as well as the diameter, and then also looking at some of the results, in this case total pressure and total temperature. We have access to all of the functionality inside of Excel, so we can use traditional Excel formulas. They will function just as normal inside of the Excel environment, as well as using some of the graphing functionality to visualize our results as well. Okay, in terms of actually linking this to our flow network, it's just as simple as dragging and dropping results. So for example, if I want to take the velocity of this channel, I can simply click on the component, move across to the Excel report, and drag the velocity results onto the Excel sheet, and this cell here becomes linked to that flow component result. As that result changes, this cell will change as well. So it's a very easy environment to take our flow results and put them into a more comfortable interface, which we can use to analyze the results afterwards. So to run our parametric study, all we need to do is run our sensitivity analysis. This will then step through each of those rows in our parametric table, and then the results will be stored inside of this Excel environment. So every single time the system is solving, you see a new row being populated here. Our solving times in this case are somewhere in the order of about maybe half a second to 1 second. To then basically give us the total results for our simulation. We see the total pressure inside of our system plotted in this column over here, which we've then plotted on this graph. In this investigation, the angle for alpha is kept constant and beta is varied, as well as the diameter. We see a highest pressure at a diameter of about 30 millimeters, with the highest exit pressure at about an angle of -30. The reason that it's a negative angle is because the minimum pressure drop occurs when these holes are reverse swept, when the angle of the holes is opposite to the rotation of the machine. So basically we did this investigation for a constant angle of alpha, but to investigate all of the other contributing factors, we moved on to additional cases. Just for the purpose of this demo, I've included just the result graphs. For varying our angle of alpha, we decided to choose a constant angle of 30 degrees for beta. Varying alpha saw small changes in our total outlet pressure. As you can see, the smallest angle for alpha resulted in the highest pressure, the highest outlet pressure, or the lowest pressure loss inside of the system. The main contributing factor for this is because as this angle alpha increases, the length of this channel increases as well. As a result, the losses in this channel increase due to the very high velocities. So we see a lower angle for alpha producing a higher outlet pressure. Once we had ideal values for alpha and beta, we could then look at optimizing our hole diameter. In this scenario, we plotted the outlet pressure for different hole diameters varying from 27 to 33 millimeters in increments of 1 millimeter, and we saw at about 29 millimeters in diameter, we would have our highest outlet pressure. It was this combination of the hole diameter and the angle for beta that basically resulted in the minimum swill ratio inside of this cavity. The higher the swill ratio inside of this cavity, the higher the windage power transfer, and as a result, the higher the pressure drop through this cavity. So it was this diameter that ultimately resulted in the lowest pressure drop through the system. Okay, so just to summarize, we were able to model our secondary flow system here using some of our standard Flownex components, using a couple of scripts for some pre-processing, and then using a parametric table for a parameter table for specifying each of the cases we would like to investigate in our optimization analysis. We then used our Excel reporting environment to view our results and then do some visualization of the results in a graphical format. Following this, we could make changes to our model and investigate some of the other parameters, moving from the angle beta to the angle alpha, and then finally through to our diameter. This type of investigation, as you could see from the solving time, could be performed relatively quickly. In terms of configuring the model, the user interface is incredibly intuitive. Dragging and dropping components from the components library is very easy, and specifying them is just a case of importing geometry. There are no CAD files required, and making changes to the system is incredibly easy as well. All right, so just to wrap things up, I'd like to point out that if you do have any questions, you can ask them in a second. Alternatively, please feel free to reach out to us at sales@flownex.com, or alternatively contact us through our website. There's a section for either requesting a demo where you can receive a short trial of the software, and we can work with you, showing you how the different functionality of the software can be used in your company. Alternatively, we can just organize a meeting to discuss some of the additional features of the software that are particularly relevant to your company. Also, I'd like to point out that we'll be at the Turbo Expo this year. So if you're in North America and are attending the Turbo Expo in Charlotte, North Carolina, please feel free to come stop past our booth. We'll have a lot of our technical personnel there, as well as some of our, as well as the personnel from our North American reseller. So please feel free to stop past and come and meet us. We'd be more than happy to discuss some of the work we've done in Flownex, as well as show you some of the more detailed features, and talk about how Flownex can help your company directly. All right, that's about it for today. So I'd like to thank you for your time, and if you do have any questions, I'd be available to answer them now.